Hey everyone, Morgan here. So today we're going to be talking about standing waves and how they're going to relate to electron orbitals. So when we're thinking about a standing wave, you can picture something like a jump rope that is going up and down. So it does have the up and down wave motion, but it's not actually traveling left to right. Now, it's possible for us to actually change the wavelengths by how we use our hand to flip the rope around. And this is kind of also like the idea of a guitar string or on a violin or any stringed instrument, where when we change the length of the string, we're actually changing the wavelength or the pitch, the note that that stringed instrument is playing. So if you find this interesting, you can go into any of your physics books, of course, and learn a whole lot about standing waves. We just basically need to understand that it's a wave that doesn't move anywhere. It just waves in place. Okay? Now, the reason we bring that up is because we're talking about the idea that came from Bohr of well-defined circular orbits. And we said that it's not right. Okay, now Bohr's not an idiot. Okay, he really had some great ideas. It's just that post World War I, we started to picture them in a new way. And what we need to think of is that that orbit that Bohr was referring to is not really an orbit with an electron rotating in it itself. Okay, the electron is the orbit. Consider the electron to be a standing wave and not a particle. See, it's moving so fast at this point that it has just kind of spread itself out over the whole orbit. Imagine if I had, a flashlight tied to a string and I was spinning it slowly. You could take your finger and you could point to where the flashlight was moving. Okay? But if I started to move it really fast, you would no longer see that point of light traveling in a circle. You would just see a circle of light. And that's what's happening with the electron itself. It is the standing wave that was the orbital. Okay? Now, this is, in essence, a probability map. We're saying this is where the electron is likely to be located in that orbital. Okay? So an electron cloud is really the electron itself. Okay? Spread out over this entire area. And it is a probability density. So we have the area where it's most likely to be found. Okay? And then as you get away from that, it's a little bit less likely to be there, but you still have that possibility. So when you look at these red clouds in this diagram on the right, as it starts to thin out towards the edge where it gets a little bit fuzzy, you're less likely to find the electrons. And where it is the darkest red, it's where you're most likely going to find the electrons. Now, Bohr had calculated very precise electron orbits and energy levels. And he wasn't really wrong. It turns out that his well-defined circular orbits actually corresponded to the 90% probability of finding the electron in that orbit. Now, 90% is pretty good. I know some of you are desperate to have, an average of 90%. So Bohr was on the road to the right place. The problem was just he was still picturing the electron as a particle moving in the orbit rather than the electron actually being the orbit as a standing wave. And that's when we changed the name from orbits to orbitals. Erwin Schrodinger was one of the first that really came up with a reasonable theory behind how this works. He was Austrian. Okay, he was a little bit older than most of the physicists involved with this. He was Bohr's age, so he was part of the old guard. So he was using very classic ideas from physics. So he treated the electron orbital with what we call wave mechanics. And again, go to your physics books and you can look up a whole lot about wave mechanics. He considered that the electron was the standing wave. And today we have the Schrodinger equation, which describes that. Okay? We're not going to get into what that equation is. It's a very complex mathematical thing. Now, Schrodinger's interesting to read about. He led what I guess we would call it a very progressive lifestyle for the time. And I'm going to leave it at that and let you go to Wikipedia. Now, at the exact same time, we have Werner Heisenberg. He was not Austrian, he was German, okay, and quite a bit younger. In fact, during World War I, he saw his father go off and serve. So he was a very loyal German. He was not loyal necessarily to the Nazi Party, although he was a member of it. He was a high-ranking Nazi. He was just more loyal to Germany. And his attitude was more, leaders come and go, but Germany itself would survive. So he stayed in Germany, and he actually led up Germany's atomic bomb project during World War II. So in the early 20s, Heisenberg was young, talented, and he kind of applied matrix mechanics rather than what you would call the classical wave mechanics to the idea. Now, it resulted in what we know as the Heisenberg uncertainty principle, which is that equation that you see on this stamp, which is actually a great German stamp. The principle states it is impossible to know both the position and momentum of an electron simultaneously. Now, what this is telling you is that an electron is so fast that if you were going to say, hey, look, it's right there, by the time you say that, it is so far gone, it's no longer an accurate description. Now, you can measure its momentum. Some people just say velocity, but really you're talking about its momentum very accurately. But the more you know about the momentum, the less you're going to know about where it is. Okay? So typically, we would say this as the uncertainty in the momentum times the uncertainty in the position is going to be greater than or equal to h over 4 pi. Now, the way it's on this stamp, the uncertainty in the momentum, delta p, times the uncertainty in the position, they call it delta q, okay, is proportional to h. And it's saying the same thing here. Okay? It's saying you can't know them both, the product of them, okay, any better than the value of h, which is Planck's constant. Now, they both received Nobel Prizes for arriving at the same idea very, very different ways. Okay, but they both ended up with the same concept about electron orbitals. Again, Heisenberg, there are a lot of biographies about him, and it's fascinating to read. I strongly recommend it. So now, as we are in 1925, basically, we have what we call quantum mechanics being born, okay? It is the study of particles too small and too fast to obey the laws of classical mechanics. Now, this is basically where quantum mechanics grows up. It becomes an adult. It was born December 14th, 1900, with Max Planck's presentation of his equation and him questioning, saying, I don't actually believe this, but this is what the data is telling me. Can you all tell me where I've gone wrong? And everybody disagreed with him. No, your data's saying this. We don't agree with it, but it's what the data's saying, and we need to pay attention to it. Now, a more complex definition of quantum mechanics, and don't necessarily worry about writing this one down. This actually came out of my quantum mechanics book. The branch of mechanics that deals with the mathematical description of the motion and interaction of subatomic particles, incorporating the concepts of quantization of energy, wave-particle duality, the uncertainty principle, and the correspondence principle. That's quite a mouthful there. I think we'll be cool with just that first one, the study of particles too small and too fast to obey the laws of classical mechanics. Okay, now this is where it starts to get important. The quantum numbers are going to answer a lot of questions for us. They're not going to be direct questions on an AP exam. They can be on a Chem Olympiad. But the background behind them will be used to answer questions on the AP exam. So there are four quantum numbers. The first one is called the principal quantum number. Its symbol is n. That's a lowercase n. It can have values of 1, 2, and 3, etc. It'll never be 0, and it will never be fractions. There will never be negatives. And the meaning is the size or energy of the electron orbital. Now, when you look at a periodic table, period 1, which just contains hydrogen, helium, corresponds to principal quantum number 1. And lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, period number 2, all correspond to a principal quantum number of 2. So the periods on the periodic table correspond to the principal quantum number. That's what we really need to know. So as the principal quantum number gets bigger, the electrons get farther away from the nucleus. The orbital is farther away, which makes it a higher energy orbital. The second quantum number is called the Azmuthal. We give it the symbol capital L. Some people use the lowercase l. It just depends what book you're reading on that one. The values can be 0, 1, 2, all the way up to n minus 1. Now again, no negative numbers, no fractions, but this time 0 is included. So the value of the principal quantum number will determine the possible values of the Azmuthal quantum number. And this tells us the shape of the orbitals. We'll look at those in a little bit. Then we have what I call the magnetic quantum number. This one has different names depending on which book you're reading. I like magnetic. Its symbol is M sub L because it's going to be based on the Azmuthal quantum number. Now its values can go from negative L all the way up to 0, up to positive L. So you have to know the Azmuthal quantum number to be able to figure out magnetic quantum numbers. And this is going to tell you the orientation, the three-dimensional orientation, what we would call X, Y, and Z when we were graphing of the orbital. Then we have finally the spin quantum number, which was the last one discovered, M sub S. It's either a plus 1/2 or a minus 1/2. There's a lot of discussion about what that means. Really, the best way for you to think about it is it's one of two states that the electron can exist in, which we now call spin up and spin down. Okay, and it's not actually the electron spinning, it's just the states. All right, so now, let's see if we can visualize this. Here are pictures of the S, P, and D orbitals. Now, the principal quantum number n is best illustrated by looking at these three spheres for the s orbital. As they get bigger, that is the value of n increasing. So you see the 1s orbital, the 2s orbital, the 3s orbital. They get bigger. 1, 2, and 3 are the principal quantum numbers. Now, L, the Azmuthal quantum number, is going to tell us whether it's an s orbital, or a p orbital, or a d orbital, which basically tells us the shape of those orbitals. Now, for the p orbital specifically, m sub L can be minus 1, which we call the 2px. It can be 0, which we call the 2py, and it can be positive 1, which we would call the 2pz. And that's why when we're talking about the p subshell, it has 3 orbitals in it: px, py, pz. The x, y, and z are just what orientation they've taken 3-dimensionally. Okay, now, that Azmuthal quantum number, L, has values like 0, 1, 2, and 3. And it can get bigger than that, but it won't for the periodic table that we're currently working with. Now, the orbital they correspond to, 0 would correspond to the s orbital. So an L with a value of 0 means it's an s orbital. An L with a value of 1 means it's a p orbital. L with a value of 2 means it's the d orbital. And L with a value of 3 means it's an f orbital. So this is why when we look at period 1 on the periodic table, which just has hydrogen and helium, n equals 1, L can only equal 0, and we can only have an s orbital. But then when we go to n equal 2, which on the periodic table starts with lithium and ends up there with neon, we've added a p orbital. So we have the possibility of s and of p. And when we get down to the third row, we've added another possibility, which is the d, and that's where all these come from. It's these quantum numbers that actually dictate how the current periodic table is structured. That comes from 1947. Okay, now getting into spin a little bit. In 1922, Otto Stern and Walter Gerlach did an experiment looking at the magnetic moment of electrons. What they took was a beam of silver atoms. And the reason they chose silver was it has 1 unpaired electron. So they figured, okay, if you have 1 unpaired electron, that will mimic what 1 electron would do. You couldn't just do this experiment with a single electron itself, but if you have that atom that has 1 unpaired electron, it should mimic it. And what they saw was that when they passed that beam of silver atoms between 2 magnets, a north and a south, and very strong magnets, what happened was that the electrons deflected in 2 different directions, and there was no way to predict which way it was going to go. It's just, as you can see in this diagram, they went to the left or they went to the right, although it's probably more accurate to say they went up and they went down, depending upon the north or south magnet. Now, what this told us is that basically electrons can exist in one of 2 different intrinsic states. Okay, today we call them m sub s plus 1/2 and minus 1/2. So one of 2 states. Now, Wolfgang Pauli in 1925 basically showed that Stern and Gerlach allow us to introduce a 4th quantum number. They said this result can be explained with a 4th quantum number. Okay, he didn't try to interpret what the quantum number meant. He just said, you need that 4th quantum number with 2 possible values, plus 1/2, minus 1/2. Now, the Pauli exclusion principle was the result of this. And that is that no 2 electrons can have the same exact set of 4 quantum numbers. And that the quantum numbers are going to allow us to describe each individual electron with its own specific set of quantum numbers. It's almost like a street address system. You're saying exactly where that electron is residing in terms of the orbitals. So, a little bit of interpretation about what might cause this. When electrons are orbiting, they are charged particles. And charged particles when moving, generate electric and magnetic fields. And sometimes they generate a field in one orientation, like the north side or the north pole of the magnet, and sometimes it's going to generate the other opposite field. Now, this is a thing really depending upon what we call angular momentum in physics. And the angular momentum quantum number is one it's a name that has been used in the past. Okay? So, Goudsmit and Uhlenbeck, 1925, just a few years after Stern and Gerlach, say that the two intrinsic states of an electron could be explained with two angular momenta, or spin states. Now, again, these are two very interesting individuals. Goudsmit ended up in the US and was taken into the US Army as basically a post-war spy. And he was the guy that was sent into Europe to try to locate all of the scientists that had been working on Germany's, just the general, their scientific projects during the war, because he knew all of them. I mean, he'd gone to school with these people, okay? And he was, at this point, very loyal to the US and very angry with Heisenberg, because he had written to Heisenberg begging him to intercede with the Nazi Party when Goudsmit's parents were taken and put into a concentration camp because of them being Jewish. Although it never happened. There's a great book out there by Sam Keen that talks about all this. The name of the book is called The Bastard Brigade. Really worth reading. Okay, now, there are going to be some questions there for you to play with in the lecture outline about how quantum numbers work, okay? And I want you to practice that, and it's something that we can go over in our next lecture. Okay, thanks for tuning in, all right? Those are the next couple of pages there on the lecture outline, and we're going to proceed next with talking about the periodic properties. Okay, thank you for tuning in. This is Morgan signing off.